Okay, so today we'll talk about soil water. Actually, soil has a tiniest particle and it has three components, as we know: solid and a liquid uh, and air component. So basically, it's the soil within the water that matters a lot, because if your subgrade soil gets saturated, it will not support your pavement. Normally, what happens that if you are laying an asphalt concrete, we heat it around 135 degrees centigrade minimum. Uh, Maybe depending on the grade, can be 150 degrees centigrade. There are polymer modified asphalt that are being heated at 165 degrees centigrade. So anyhow, so all that water get evaporated or get dried. So that's why if you have a coarse grained soil, you may not have the problem. But if you are encountering fine grained soil, and with a bulk quantity of mineral fillers, that is minus 200 soil, then there's a problem. That water cannot be dried out at any temperature. So this is an indication that we must know how soil water interacts, not only inside it and also outside its particles. So as we know from our basics undergrad course, that soil contains three components: solid, liquid, and gas. The solid component are weathered rock or sometimes decayed vegetation. The liquid component is almost always water with the dissolved matter, and the gas component is air. So this ocean of water and air, this volume is known as the voids. The spaces, the pores in the soil particles. These soil particles, if they are used as an aggregate, they will absorb your asphalt. But if they are not used as these soil particles, these voids, if as they have water, during a cold region, the cold weather, the water, the entrapped water will turn into ice. And eventually, in summer, that ice get broken and consequently resulting in the breakage of the soil particle itself. So assuming that this is a 1 cubic meter of a soil, we idealize it as a cubic component. So it's an idealization, the soil is not cuboid as I've shown. There is a solid and there is a void. So as water in a given soil may range from virtually none to saturation. And when we say saturation, we mean even the air component is filled with water. These solids are only partially filled with water. Soil is said to be partially. If you assume that there is solid and there is water and there is air, then it's partially saturated. If I say if even the air has been replaced by water, then it's fully saturated. So the characteristic of soil is influenced by its water content, especially what we fear is about the performance of fine-grained soil. A clay soil seems hard as a rock and it's dry, but becomes soft and plastic when wet. This is a problem. In a contrast, a very sandy soil, such as we found on beach, may be relatively loose, but hard and more stable when wet. So the study of the soil mechanics critically revolves around the effects of water in and around it. Even, while we design a pavement, we assume that the pavement is laid on a wet soil. Even though that, that wet session may be maybe once in a year, like in Karachi, monsoon, July, maybe September, August, and maybe in third, maybe years. But even then, when we design a pavement, we always assume a saturated, not saturated, but a wet soil. And that is where we find its strength in its wet condition. Logically, if you design a pavement considering a dry soil, with all things constant, as compared to the pavement designed for soil and dry condition, you will end up with more thickness. But again, because of the undefined, unpredictive nature of the soil with exposure, with influence of the water, we don't take risk and to design a pavement for a dry condition. Another problem, that's why it is dangerous, and we just keep on saying while I'll be teaching, we will learning this course, that we are afraid of the cohesive soil because it tends to shrink when dry and swell when wet. Some types of clay expands when it's saturated. Look, this is if you talk about compare the water in the soil, you can define 4 regions. There is this portion called saturation. You can see this excess of gravitational water is very less in a silty clay as compared to the sand. Then there is an available water with no plant stresses. There is available water, plant stress possible, and there is unavailable water. The most problem, that's why if you're not an engineer, if you are talking about agriculture science, they will prefer all this type of soil. As a reverse, we want this water to be as less as possible. So you can say one of the water that is in the soil is a hell water, and that is there in the soil, always in the soil. It's a part of water held in soil pores by some force existing within the pores. It is not free to move under gravitational force. It can be in structural water, adsorbed water, and capillary water. When we say structural water, it is the crystal structure of the soil. Normally, if you try test a soil, there's a terminology that has been always asked: oven dry the soil, 105 to 110 degrees centigrade. That structural water, even it cannot be removed with that dryness. It will be there. Then there is adsorbed water. It's a part of moisture when the soil particles free adsorb from atmosphere, and that is the force of addition, and obviously this is the water that can be removed while you do the over drying, so not over drying. Then there is a capillary water, and this is the problem that this capillary water is more dangerous than any other water because the water outside is the interests of the soil due to the force called capillary water. The capillary and gravitational water is collectively called pore water, free of strong soil attractive force. When we say capillary, it means rising of water in a tiny hair-like spaces above the level of the root. And why there is a rise? It's because of cohesion of the water molecule and adhesion of the water to the tube walls. See this diagram. You see, this is a very fine tube. This is in middle and this is a large diagram. So if there is a water beneath it, assume a tub full of water and you have inserted these three capillary of varying size, you will find naturally the thinner the tube, the more rise. And now assume this as a fine grained soil. You have water beneath it, and you have a fine grained soil that are very less in space, right? So naturally, if the water table, this water table will rise to the surface, to the bottom of the pavement. And that's why one school, a thumb rule of constructing a pavement that has high water table is to do it in embankment and at least 1 meter above the existing groundwater table. When I say 1 meter, I mean the depth of the subgrade. So I'm not talking about top of the pavement. And if you talk about an idealist design that is around 0.6 meter or 0.7 meter. So in this scenario, you can say the top of your pavement is around 1.7 meter, 1.8 meter above the existing water table. So this is one way of avoiding the capillary action in a soil. But even then, when we do embankment with a coarser material. It's not that we construct an embankment of a clayey material or fine grained material. They are on the coarser side. Because we want this width between the gaps between the soil so that the water force cannot generate. One thing, I just keep on saying because I want you to remember this ever in your life, that this is the big problem in a pavement. Your first option is to have an embankment. But if you are talking about constructing a road in an urban environment, you have lack of spaces. There you cannot have embankment as you decide. Or you can have embankment, then your embankment will not be an earthen embankment. It will be a concrete encased, and it's a very high cost concrete. Because normally you have an embankment of an earthen material. They have a slope around 2:1 for stability purpose. So, if you have, say, 5 meter, for example, if you want to have 7 meter finished road, and then it's not 7 meter you required. At the bottom, you may require 10 meter, 2 meter here and 2 meter here. I am assuming that the pavement is only 1 meter high, right? So if I is 1 meter high, obviously 2:1, 1 meter here and 1 meter, 2 meter and a 2 meter here. So actually at the bottom I need 9 meter. At the top I need 7 meter. So if we have this 9 meter, extra 2 meter available to me? If it is not, then my desire of constructing an embankment to avoid this capillary water may not be achieved. So then I look for the solution. One solution is to have a French drain. French drain, I mean within the subgrade, just below the subgrade, you dig a trench, you lay a horizontal pipe, they are porous pipe, and you try that whenever the water is rising, these holes will never let it rise. And gradually, the water table will be lower. What happens when the pavement becomes dangerous is when there is a rain. Eventually, the groundwater table started to rise. And our problem is if we do not trap it, the pavement, whatever, there is no impervious pavement as in the world. Even though you assume it is to be impervious pavement, it cannot. Some water do go inside. The problem is if the water go from inside, and obviously the water will also flow from the sides as well. So these water will get the existing water to rise, and it will create a problem. So if we have applied this technology of French drains, then we can tap this water. So this is one thing. But imagine that if you have this problem, say 5 kilometers within your highway section, constructing a French drain will be very costly. Another cheapest way is to pump out the water. But how much water you are going to pump out? If for the sake of construction, you can do it. Say for just keep on pumping the water till you have a foundation and then you do it. But at some time you have to leave the water at this. So what you do, you may replace some soil as well, replace it with the coarse gravel, improves the grade. And people are now using synthetic as well. So, but at the end of a time, and sometimes what people do is insert those capillary pipes and leave it for years. So all the water like this sucked out, and that can be pump out at our wells. But again, this you need this happen. We're talking about futuristic system. We're talking about road, not emergence road, maybe sometime later. So, and sometime with all this embankment, we also layer an asphaltic layer so that it becomes impervious. It's just like when you have a water within the building, you have applied PVC to protect it from the moisture. In the underground water tank, you apply PVC. This also, right? The point is, the understanding is, don't let capillary force to occur within your soil, within your pavement, because it will damage your pavement. Now, if you consider if it is a loam soil, and in this in the context of uh, you know of plant agriculture engineering, this will have about 11% volumetric water content at melting point. So you must be wondering, the topic of loam soil doesn't occur to us why we are studying, but still very important, because if you see an excessive plantation within your alignment, you find this type of soil. Again, this type of the soil will never ever be allowed to occur in your pavement, because it's the problem. And even with all this science, with all those teaching, I have witnessed a pavement in which after constructing the pavement, the plant has actually grown out. And I just kept wondering what happened. Actually, people ask me, sir, look at this, you are a pavement engineer. We have constructed a pavement and the plant going out. So there is a very simple reason. If you look at the construction of the pavement, if you are asked to do construction, the first step is to remove debris, remove the top soil. Because there, if you have a grass on that soil, it means it's a loamy soil. And even if you construct a pavement without removing it, you have to just remove that top 6 inches of the soil, no matter what happens. Even after 6 inch soil, you may have a rock. But remove that 6 inches of soil, because this will happen. The first point in any construction, highway construction technique, is to remove an excessive soil, top soil. And if you don't remove it, there is a plantation. It's very strange. Then you stop wondering, because the contractor is always in a hurry. He removes something and he will leave it something. It's about the supervisor to take care. And sometimes you will think, contractor saying, sir, that's okay, sir, that's okay. But that's not okay. Move that soil, dump it somewhere. Sometimes what happens during the embankment, you cannot stay on, even you have a camera, you cannot put cameras. We don't have a practice of putting cameras on site construction. So if you do not stay overnight, because these contractor people just keep on putting everything in the nearer to make embankment. Even the topsoil they have removed for the pavement right of way, they may put it back. That's what happens, that the rain comes. No matter how much impervious you claim the pavement is, the water will penetrate through that things. And if it gets soil, you must have seen the what plant growing out on the embankment. And the reason is what I am saying to you. So be careful when you, and the best thing is to check every time is take the sample. Always take the sample. Check your embankment. Take the sampling. No, do not let people dictate to you. Even though he's very honest, ask him, I need a sample. Take a sample out of it. Maybe 5 kg. 5 kg will be enough for sieve analysis. No, do nothing. Just go and do sieve analysis. There are 8 sieve required. It's it's a 1500 rupees test. In this in these times, 1500 rupees. Spend 1500 rupees, and you will find that what type of impact material that the contractor has done. Basically, we don't check it. We thought it will be covered by stone. Nobody wants to check it. But it's not there. This, I think, phenomena I explained to you how the water rise in a capillary tube of surface tension. What we fear is in the gold region, the frost section and frost seam. Frost section is a phenomenon that occurs in the winter and early springtime in northern climates. Practically all surfaces, soils undergo some frost section depending upon the local climate and obviously the amount of precipitation they have in terms of snow. Frost actions divide into 2 phases: freezing the soil water and thawing. It's a thawing that we fear, because whenever the water melts, it needs more space. And to need more space, it is in the limited place. It will exert the force on the walls, and consequently, all the pressure will be transferred to your road surface, and you will find your pavement broken from this section. And especially the concrete, the concrete pavement. The only thing that breaks the pavement, that hurts the concrete pavement, is not the traffic load. It is climatic load. You must be wondering whether this frost heaving is dangerous to an asphalt concrete. Yes, it is. But comparatively, because of low coefficient of thermal expansion as compared to the thermal expansion of cement concrete, the loss is minimal. Though we have a transverse cracks, but they are not structural cracks. But in a concrete pavement, that is a structural crack. So, even with all these things, all the advantages, we always the side of constructing a rigid pavement. If you have the climate such as this, you must be very sure that the soil within the concrete is not a clay soil. Let me emphasize what I am trying to suggest here. Normally, The pavement support on a separate soil for a concrete is very minimum. We do not require the much of the soil support as compared what we depend our dependence on a flexible pavement. So whenever in our country you find that the soil is very weak, you cannot construct the embankment to go for a concrete. It will do two things. One, it will absorb your overloading. Secondly, it will take care of a fine grained soil as well. But if the same thing happens to somewhere where you have a temperature around the year less than 0 degrees centigrade, then that concrete pavement will not help. That's where the point of discussion of today is. It's very important to know the climate of the country where it is. Not always say concrete pavement is superior to flexible pavement. Not always say flexible pavement. Sometimes because of the local condition, with all the available resources, you have to make a compromise. Go for flexible pavement or a rigid pavement based on the climate of the country. Climate is one of the components. So, what are the energy concept? Water moves from high to free energy, from wet to dry soil, large pores to small pores. Water free energy is higher, water free energy is lower, and this is the energy that causes water to move. So if you look at this energy level, there is on the positive side this gravitational potential, and on the negative side it's an osmotic potential, and this is the pure water elevation. People have drawn this water retention curve. Obviously, the sandy soil, the suction is less as compared to getting water out of clay soil. You need to have a more effort. Now, saturated flow through the soil factor influence the hydrolytic conductivity of the soil, the size and configuration of the soil pores. Macropores account for most of the saturated water flow, texture and structure, osmotic and nature of inorganic type of clay, differential flow, sandy soils, and the clay soils. When we say infiltration, it means the difference between what is the difference between infiltration and percolation. The process by which water enters the soil pore, this is called infiltration, and it is centimeter per height. It decreases during a rainfall or irrigation episode. Pores, especially in subsoil, filled with water. Pore in subsoil smaller than surface soil. Clay may swell upon wetting and reducing pore size. When we say percolation, it's a downward movement of water into the profile. So it involves both saturated and unsaturated flow. Usually appear to be sharp boundary. Percolation rate generally decreases in depth, and it's generally during a rainfall or irrigation episode. And when we have a stratified soil, most water, it's now what all these we are talking about, discussing the type of the soil strata we have. Most downward soil is by unsaturated flow, have a very profound influence on the water movement. effect is usually that of barrier to downward water movement. Impervious clay hinders downward movement. Sand or gravel layer will also act as a barrier to water flow, causes soil to be unexpectedly wet or for longer period. The problem is if you have a water, if it rain, the water will go down, and if it is not allowed to go down, it will trap within the soil. Trap in the soil, it will keep the soil wet, and when it keeps the soil wet, whenever the load is transferred from the pavement to the soil at places get settled. It's just like imagine you had a utility service work in the area, and whenever there is a rainfall, you will find the trench within that portion. You can easily identify where on the road your utility services was laid, because this is the portion where this, because it had, after filling most of the time people don't use that, you know, drain soil. They use uh, what we say uh, no stone soil. They don't use no stone soil. They dump whatever they have excavated. And what happens that once, even though they do an compaction, but that compaction is temporary. And when there is a the water, the soil within those stones get washed away. Consequently, you have holes, you have pores, and the pavement settles on those areas. So allow the water to go through. If you don't allow them, they will retain, and then there will be a problem. Pavement will settle down. So there's a concept. Imagine you have a sandy soil or a clay soil, the water flow down. If you have a clay soil or sandy soil, the water will try to flow down, but it will retain on it. What about if there is a clay soil, water will get trapped, and not only the water flow from the top, the water will also flow from the bottom because of the clay to reach the sandy layers. So you see, if you look at this thing in terms of the bars, how much pressure you need, physical, no, gravitational, soil and biological soil, you know. There is a gravitational, there is a capillary, and there is a vapor. But for your biological soil or peat soil, there is unavailable water, there is available water, and there is unavailable drainage water. So what happens during a frost action? There are three conditions of which must exist before frost heaving can occur. Sufficiently cold climate to allow freezing temperature to penetrate below the surface into the base. Sufficient a supply of water from below or into the freezing zone or capillary water, you can say. A material that is frost susceptible and lying within the freezing zone. And it's what we say that water expands 9% by volume when freezing. And this is the size of an ice that depends upon the quantity of free water available within the soil. Once started, ice losses continues to grow as longer as the source of free water is available. And this migration of water can be as far as 20 feet for certain frost processing. So eliminating of the supply of water to the soil below the pavement is virtually impossible. Our good drainage can partially reduce the quantity of water available to feed an ice lands and cause frost. Some soils are more susceptible than others. Obviously, the fine grade soil or clay or silty soil are more susceptible than the other soil. So this is on the left side, you can see this is a wall, this is a ice land formed because of the water percolation from the top of the pavement. And its size is growing because of the groundwater table. This is the where you will have a crack. So the only soil that can be considerable are mixture of sand and gravels. So where it founds, transition from cut to fill, ditches are inadequate, over culvert pipes, adjacent to driveways, dam roadsides, wherever there is an abrupt change in subgrade material, we have this frosting problem. So they say if the reaction frost saving is uniform, there are no bumps or hole, there is no problem. But heave is destructive and troublesome during the freezing of frozen phases where it varies sharply, causing uneven support. So again, we start with this point, we end always this point. If you have a soil having CBR less than 5, your soil have a cohesive nature, the soil, you have clay and silt, get rid of it. In every climate, this is the same formula, irrespective of the climate, irrespective of the region you live. If you have a subgrade soil, you have a cohesive soil, get rid of it. If you cannot get rid of it, then don't leave and don't start constructing pavement as it is. Do something with it. Stabilize it, remove it, overlay it with some material, improve subgrade material, use concrete pavement, use French drains, do something. Don't take it easy. So let's see. Let's try to again uh, classify the soil on the basis of frost potential. A1, A3 soils are very good. You don't need to worry. Their frost heat will not occur. Uh, there's a chances if you have something A2 soil, the chances are less, but still there are there. But if you have anything A7, A6, A4, A5, you have a problem. Comparatively, A7 is more dangerous, A6 more dangerous as compared to A4 soil. What is an ideal soil for pavement construction? Actually, A3. A3 is a very ideal soil. Though we want to have A1, but these are very, very ideal conditions. Even sometimes when we ask undergraduate students, we ask them use choice, design a pavement based on taking soil of your own choice. So the intelligent student take A3, and some people take A1. That even that's okay. But anything A1 and A3, people take A2, A7, this weightage of the mass grade is become less. So for frost safe, provide drainage for base and surface layers, use of capillary cutoff, design the pavement for thaw action that is providing more expansion, less stable, flexible base. Next topic is today is a very important topic, is the site exploration. Very, very important topic. Most of the time, you are working as a graduate, you are working as an executive engineer. You have to make a project estimate, and then you've been asked to do the project. Obviously, if you're even talking about highways or a building or a bungalow or any project, any infrastructure or big project, this is the detail of the thing that you must know to ask to be a part of your contract. What we want to explore the soil, define the depth of the proposed foundation, evaluate the load bearing capacity, estimate the probable settlement, identify potential foundation problem, define groundwater conditions, predict lateral earth pressures, determine suitability of the site material. So it contains data collection, terrain analysis, site recce, subsurface sectioning, and sample recovery. So the data collection depends what type of structure you are having. General use of the structure, column load, column spacing, building code, basement requirement, topographic map, geological map, soil map, groundwater maps, reports, aerial photographs, satellite images, etc. When we want terrain analysis, we want to know the geomorphic characteristics of the soil. What I mean by geomorphic, what is the soil strata over there? There are clay, the sand. What is the horizon we were talking about in the earlier part of these lectures? Amplitudes, drainage basins, vegetation, climatic conditions, weathering, cross section, erosion. When we go for site recce, we want to know the general topography, the existing of drainage. We need to know the profile. We need to have the general condition of the soil, the vegetation around it, surface water condition, how you can assess the site, from where you can access. For subsurface, you want to know the seismic reflection, test pits for shallow depth. We use test pit for the pavement testing as well to take the soil sample. Auger boring, wash boring, core boring. Again, what depth you want to have is depending on the type of the construction, the column load, and the column spacing. So, in planning and executing, you need to know equipment selection, bore spacing, and boring depth. This depends on the terrain features, accessibility, geological conditions, boring depth, sample types, and nature of the project. And this is a table I think you must have in your life all the time if you are working as a consultant. You see, the spacing usually range from 30 feet to 1600 feet. For multi-story building, you have one hole between 30 feet to then 200 feet. If you have, say, you're talking about, say, area housing society or residential subdivision, you can have 800 feet at least. Then warehouses, 60 to 1200 feet. Dams, 130 feet. Highways, we have 800 feet to 1600 feet. Obviously, this depends upon the size. So you start with 800, and at 1600 you find, at another 800 you find uniformity then don't go for 800, go for 3200. This is how you gradually move. Or naturally, you are not going to explore every inch of the land you have to construct. There must be soil sampling. And based on these spacing, you draw your project estimate. Because if you ask your contractor to do the soil exploration and you do not put the cost, then you cannot assume yourself that the construction that has been taken place is based on the true value of the soil. You don't pay, you will not get. And these are the costs that should be included in your project estimate. I'm talking about the public sector projects. These costs must be included. Even a private sector project, even you have a normally for Bangalore, we don't take care of this amount. Don't put in our view. Should be there. So what should be the depth of the boring? Again, this is a very good literature. It says that through any unsuitable foundation until soil is accepted where is reached, extended to 1.5 to 2 times the minimum width of the loaded area. This is another way. In case of very heavy bridges, boring cases are extended to bedrock. At least one boring should be extended to the bedrock. The following empirical relation, depth of boring is 3 times S into 0.7. What is S into 0.7? S actually, I'm sorry about this, typo, actually S power 0.7. Right? So for light street, it's like this S is the number of stories in meters. Right? And what is the sample recovery? Soil samples are either disturbed or disturbed sample. So disturbed sample, you do it for grain size analysis, index properties, organic content, specific gravity. For undisturbed sample, we can determine the mechanical properties and as well as the hydraulic properties of the soil. How you do it? By hand, if you're talking about the trenches, but split spoon, scraper bucket, thin and water tube, Shelby tube we say. Then there is a split sample method to obtain disturbed or undisturbed soils. It's an SPT test, a common test we all know. So this is a SP test which was developed in 1927. It's again now, even in this, after 100 years, 200 years. So it is estimated the testing is standardized. We use a 140-pound driving mass falling from 30-inch, drive the standard split sampler, 18-inch into the soil, counting the number of blows. Till you find these reports. Boring should be refusal, should be halted. If 50 blows are required for any 150 mm increment, 100 blows, the more the blows required, it means the harder is the soil is. The less bore means the soil is soft. And this is the pictorial representation of that soil. This is a typical 1-inch rope person. This is a 30-inch fall, driving, and like that.